I don't want you guys to be rushed, so I'll probably add another week to it. We'll just see how next week goes. So the other thing I wanted to say was, yeah, I felt I rushed a little bit last class, so we're gonna kind of take our time today, and that's another part of the extending. I just want to make sure that we're getting through this material nice and smoothly. And I don't want to throw too many things at you at once. I think this is a really important topic, and I want to adjust my schedule a little bit. We're actually ahead a bit from last year, which is good, maybe by about a lecture and a half. So what I'm going to do today, we're going to continue with angular momentum, talk about it in the context of the electron. And then we're going to talk about another type of angular momentum that the electron has that we'll get started on, which is spin. And so usually I teach spin at the end of the hydrogen atom, but the first problem on the homework is a spin question. So maybe we should do spin first. And spin is a natural extension of this conversation. Okay? The rules of spin work the same way as angular momentum. There's just a couple of fudge factors that we have to deal with. Some slight differences in the way that we set up the problem for spin compared to this orbital angular momentum, as we call it, which I'll define today. And so we'll talk about the similarities between the two. And this will bring us back full circle, hopefully by the end of this lecture, to color and flavor. What we're actually talking about this whole time is the theory that we've talked about for color and flavor. All right, you guys have actually seen this stuff before in a slightly different context. So hopefully you can start to get some connections between the concepts from the beginning of the class and then the real meat of the electron today. Okay, so we're talking about the angular problem in the hydrogen atom. Remember, we've separated, hopefully one of the things we take home from last class is that we're separating the hydrogen problem into two parts. One is this radial problem, right? This pull from the electrostatic potential between the proton and the electron, right? Which is only a function of r, the distance, which is a rate, which of course is radial, right? It's not dependent on angles. And then we also have to consider the motion of the electron in terms of its angles around the proton at fixed distance, fixed r, which leads us to this idea of angular momentum. The idea is that we have, in some sense, some sort of connective, a connective spring of some rigid bar between the electron and the proton, and we're spinning that electron around the proton at some momentum. Okay, and let's just kind of go through the physics very quickly for angular momentum. Again, the nice thing is we'll see that we don't really have to think about cross products and vectors and things too much in quantum mechanics, but it's nice to go back to that approach. The angular momentum of an object that's attached to another object connected by some barbell or something like that with length r. Well, if we define a vector, a displacement vector r, and we give the electron some momentum, some velocity in some direction, right? We give it a kick to get it spinning. And we have some velocity vector v in some direction. The angular momentum is the cross product of those two vectors. And remember, the cross product gives you a vector that's perpendicular to the two vectors that you're crossing. And we use the right-hand rule. So we have r coupled across r cross v here. And that means from the right-hand rule that the angular momentum is pointing out of the board like this. Okay, so we have this new vector L that's perpendicular to r and v, and therefore it's sticking straight out of the board. I can't really draw that particularly well, but I'll try my best. Do it like this instead. Sticking out of the board. And the interpretation of this vector, this is the direction that, right, in some sense, the angular momentum vector is tangent to the trajectory of the electron at that point in a circular motion, in some sort of orbital motion. So what that means is that the electron instantaneously is moving out of the board. Right? So the effective motion of this electron, this particle with an angular momentum vector in this way, is it's moving in an orbit out of the board and back into the board, right? So it's having some sort of circular orbit around the z-axis, right? And it's out of the board, so it's moving clockwise. It's moving like this. Right, if I were to put the velocity vector in the opposite direction, well, then I would have, it's kind of hard, I would have this instead, my angular momentum vector would be into the board, therefore it would be processing in the opposite direction, counterclockwise. Right, so this cross product of these two vectors leads to some angular motion. All right, we can always calculate the kinetic energy of anything that's moving, and the kinetic energy is equal to the square of the angular momentum divided by 2 times the mass of the electron times r squared, which is the moment of inertia. And we can promote this into an energy operator in quantum mechanics, right? We see that we have a kinetic energy. So all we have to do is say, hey, the total energy of this system is its kinetic energy. We promote kinetic energy as an operator, which we give this L squared operator. So we have this little measurement box that we've created quantum mechanically that reads out the square value, the magnitude, the absolute magnitude of the angular momentum. Right? Notice that it's squared, so we lose some sense about the direction in which it's oscillating. It's just L squared, it's just about the total momentum, in some sense, the speed, the angular speed of the system, L squared. So we don't really know if the electron is moving forward or backwards, but again, in some sense, it doesn't matter. Going clockwise or counterclockwise, there's really no energetic preference. They both have the same kinetic energy. Right? So the fact that it's squared leads to that we have this symmetry in some sense, that we have equal opportunity to go in a clockwise way or a counterclockwise way. So we lose some directional information, but we get our energy from it. Right? And the solutions, right? So what we want to do, right, in quantum mechanics is we want to find wave functions that when we measure L squared on them, we say, hey, this electron, ask this electron, hey, what's your angular momentum squared? We get a value back from the box, and then we get that electron out unchanged. Right? The quantum measurement theorem. Right, so we're looking for, right, the goal is to, that we came to the end of class, which I kind of rushed through. Goal is to find wave functions such that when I apply L squared to the wave function, I get some angular momentum back, some number, angular momentum. So some number, we'll have to figure that number out again, times psi. Right? Same problem we always have, right? And so I went through this really, really complicated series of math steps that I kind of highlighted to you, and I told you it doesn't really matter what this math is. We're not going to really work with it in detail. We really want the solutions. And the solutions end up being very, very nice. They're well-known functions that you can look up on Wikipedia, for instance. They've been known for hundreds of years. And the solutions to this problem, we have a wave function or wave functions. They have 2 labels. They have 2 numbers now, or instead of like the particle in a box, which just has n, or vibration, which just has v, these quantum numbers. Angular momentum has 2 quantum numbers, which we'll call L and M. Right? And this is a function. Psi is a function of the 2 angles, theta and phi. Right? Remember, the idea is that this is a wave function that is 2-dimensional, has 2 independent dimensions, and therefore has, in some sense, 2 quantum numbers, is 1 for each of the degrees of freedom, each of the dimensions it's free to move in. And that's generally true in quantum mechanics. You have every degree of freedom you have, what variables, every number of variables that put in your wave function, you're generally going to have a corresponding equivalent set of quantum numbers associated with it. So we have 2 degrees of freedom and therefore 2 quantum numbers. We'll talk very, very, very detailed today about what these 2 numbers mean They have very deep importance in chemistry. These wave functions are these special functions we call the spherical harmonics, which are traditionally labeled Y, big Y, L and M, the two labels L and M that are written like this. And it's a function of theta and phi. That's theta. Like that. And phi. And these are called the spherical harmonics. All right, we can look at some functional forms of these. All right, we can look at what these look like in functions. Again, I think it's best to look at pictures first, which is what we did at the end of class. Hold on, it says I've been signed out. Is that true? No, okay, we're still on. We're still live. All right, we have these spherical harmonics. And let me show you a nice, I found a nice picture yesterday of the relevant spherical harmonics. Bring it over, my other slide. Let's see, we was lecture 15, section 1. All right, I guess it's going to make me copy it from the original source again. Sorry, it's just a sec, guys. Right, so let's look at these pretty pictures of the spherical harmonics. And this picture doesn't come from anywhere more fancy than Wikipedia, so not doing anything special here. Copy the image. Why is it not? Oh, I see why it's not copied. Okay, hold on a second. This worked just fine last class. There we go. Okay. Yeah. Oh, and it crashed instantly. Great, that's lovely. Thank you. All right, well, let's just look at it on the browser for now until I get this up and running. Yeah. All right, so the Wikipedia, this is more of a traditional label for it. We chemists would typically use the letter Y, but mathematicians usually use the letter P for the spherical harmonics, but it's the same idea. Let me go ahead and pull up my graph. All right, well, I lost that. Okay. So they're labeled again with M and L. And so we index, the main index for kind of the main quantum number for angular momentum is L. And L can be any number 0 or greater, any integer 0 or greater. And M in some sense indexes the individual substates for each L. So every L, every state with a given L, say the electron is in L equals 0, there's exactly one kind of state that it can be in with L equals 0, which turns out to be what's called M equals 0, this state, which is what we identify as an s orbital. Classically, the spectroscopic labeling for the orbitals, the atoms, s, p, d, f, g, h, i. And so a system that has an electron has 0 angular momentum, it's in its ground state, is in an s state, which has a spherical symmetry. What this means is that the electron, in some sense, this is telling you something about the angular distribution of the electron in the atom, where you're going to find it. And an s orbital implies that the electron can just be anywhere, right? It's uniformly in a sphere, somewhere on a sphere around the proton. It could be anywhere, right? Some undetermined probability. It's well-determined probability, and it's the same at every point. Okay. Right, and then we can keep going down, right? We go to the P's, which is L equals 1. That's consistent with 1 unit of angular momentum. We'll go through that math in a second. And when you have L equals 1, there are 3 different values of M that are allowed. -1, 0, and +1. We'll go through that algebra, I promise. And these correspond to the p orbitals. The p orbitals are not spherically symmetric. And this is why, one of the reasons why it's called p is that they're polarized towards a certain axis. Right, so what this, for instance, this one, imagine that the z-axis is going up and down here. This orbital in the middle, if our electron is in this state, which we would call the pz orbital, the 2pz orbital in chemistry, means that the electron's angular momentum vector tends to prefer to stick somewhere near the z-axis. Right, these tell you the point where the point the vector, the angular momentum vector is pointing. Okay, so what this is saying is that in the pz orbital, the electron prefers to have its angular momentum vector pointed towards the z-axis, and that means that the electron effectively is precessing around the z-axis like a top. And then there's one for the x and one for the y. And those are insinuating states where the electron is oscillating or orbiting around the x-axis of the proton or the y-axis. Well, let's look at these a little more carefully. Let's go back to this math. Let me go ahead and save this so it doesn't crash on me and I lose everything. Oh, in fact, this is the same. Oh, sorry. This is it. Okay. Let's bring this back. Okay, great. I've lost some things, but that's okay. All right, let's talk about the two quantum numbers associated with these numbers, and let's get a little sense of understand a little bit about what these numbers mean. Angular momentum quantum numbers. I think the best way to think about the quantum numbers is to, again, it's just worthwhile to think about vectors again. Right? And what I'm going to choose to do this time is I'm going to move my axis system so that I'm standing on the electron instead. Okay, so I'm going to put the axis system here for the electron, and just draw all my vectors from the origin, just to make things easier. So we have some angular momentum vector L. That's in some direction. We'll just say the electron is right here. And we have this angular momentum vector L. Okay, we can always write, right? If this is a classical vector, right, we can write three components, right? We could write, right, we could measure the z component of L. And we can measure, draw this out. We can measure L sub x, which would be this value right here on the x-axis. We can also measure L sub y. We can measure three components, right? And that will tell us a little bit about how the electron is precessing around one of these axes. The way I've drawn it right now is that the electron is around, remember the angular momentum vector, the axis of the rotational motion is perpendicular to that axis. So if the L is pointing in the z direction, what that means is that basically the electron is precessing and orbiting around, primarily around the z-axis of the proton. And this L vector is kind of precessing in this direction. So I could certainly draw it like that. That's one option. I could have some sort of precession like this. that way. But as you can see, there's other ways I can spin this vector, right? I can also spin the vector around the point x. And I can also spin the vector around the point y, right? So there's, in some sense, 3 different ways to choose rotations. I'll do them in different colors. It could also be orbiting around the x-axis. So it's going to be going clockwise this way. And it's a little hard for me to draw it around the y-axis, but theoretically it can also be oscillating around the y-axis as well. Yeah, go ahead. The right hand. So if it's pointing this way, my velocity, if my r is in this direction, angular minimum, so r is in this direction, and v is in this direction, which means it's moving in this way to the left. It doesn't really matter. The point is, it's ambiguous. It doesn't really matter whether it's going clockwise or counterclockwise. I'm just going to make a choice. Okay, because they have the same energy. So I have, in some sense, I have a choice, right? So I can define an L, right? But it could be theoretically rotating around any of the 3 axes, right? So I have a bit of an ambiguity, right? If I fix L squared, right? That's what I'm doing. I'm spinning it up with some fixed amount of L squared. I have an ambiguity whether L refers to X, Y, or Z rotation. So what I'm going to do is, and in some sense, it doesn't really matter, because if the electron is, let's say, for instance, oscillating around the x-axis, I can make it oscillate around the z-axis by just rotating the whole thing 90 degrees. Right? So in some sense, it doesn't really matter whether it's going around the x or the y or the z. I'm just going to pick one that I know it's awesome. I'm just going to say, hey, the axis that it's always rotating around, I'm just going to pick one. I can always choose one, and if I don't like the one I like, I can switch to another one. Because they're just labels for coordinates. Okay, so in some sense, it doesn't really matter whether I do x, y, or z. I just need to pick one to be consistent. So what I'm going to do is I'm going to choose L sub z as the axis of rotation. Or sorry, not L sub z. I'm going to choose z as the axis of rotation. Okay, so whatever rotation I cause to that electron, whatever it's going to do, I'm going to say, hey, we're going to reference it relative to its precession around the z-axis. Right? The z is going to be kind of like my chosen direction for rotation. Right? So what I want to do is I want to measure, right? So if I want to know exactly how this thing is rotating, ideally I want to measure L, and I also want to measure LZ. Right? I want to know how much of that rotation is around the z-axis. Is the molecule precessing in the xy plane, or is it tilted a little bit and like the Earth is on a slight tilt and oscillating around its poles? Okay. There's lots of different ways that it can rotate. Same amount of angular momentum. So I'm going to choose Z as the axis of rotation. All right, so I'm going to build 2 boxes. Right, build 2 quantum boxes, 2 measurement boxes. I'm going to build one for L squared, right? Because I know I get that one for free. That's one I get from the energy. That's how I define my wave functions. And then I'm going to measure one for the angular momentum along the z-axis, the z component. So what happens when I apply, right? So what happens when I apply L squared to my wave functions? which has labels L and M, are spherical harmonics, right? What do I get back? So I put it into the box, and it turns out that you get a very, very nice answer. You get h bar squared. And it returns the value of L times L plus 1 times the wave. All right, so this number L that labels my states is something that tells me about how much angular minimum I have. Right? Total angular minimum. How fast am I moving? How fast am I rotating? So L, in some sense, gauges that total angular minimum. Right, so we call this L number for the hydrogen atom. Let's call the orbital angular momentum. And L can be any number 0 to infinity. So L measures something about the magnitude of the angular minimum. Right? Remember that angular minimum is a vector, so it has a direction, but when we square a vector, we just get a scale. Right? So it's just a number. Just something like a magnitude of the length of the vector. It's the square of the length of the vector in some sense. So the length of that vector, in fact, is h bar square root L plus 1. Second, it says that this implies that the length of L is h bar times L plus 1. Okay. So this L number gives me a sense of how much angular minimum is, how fast it's spinning. Well, what about LZ? Well, LZ measures the Z component of the angular momentum. And you get back an even simpler formula. You get h bar times that number m times psi L m. Right? So m tracks basically how L is pointing relative to Z. So for instance, if m is 0, then L is lying directly along x or y, right? So the xy plane, and that means that the electron in some sense is orbiting around the x-axis. Right? But if LZ is very large, then the vector is pointing towards the z-axis, right? And that means that the electron now is orbiting, in some sense, precessing around the z-axis, which is pointing straight up. Okay? And m can only take certain values. M can only be between minus L plus 1, L minus 1, and L. So it can take any value between minus L and plus L. Right? And we call M, not X, sorry, that's the wrong letter, the azimuthal quantum number. Does anyone not, maybe you guys don't know the word azimuth, it's kind of an old term. Azimuth is the term that astronomers and navigators use for the highest point in the sky. The azimuth is straight up in the sky, right? Top of this 90, go from here, go 90 degrees up from the horizon, that's the azimuth. Right, so M specifies in some sense, right, if you think about Z being the azimuth, what the projection of the angular minimum of the azimuth vector pointing towards the top. So top Z is. And M can only take certain values. Yes, ma'am.
You're saying so the LT is larger than about the CM, like the ball LT.
Yes.
And if it's 0, you said it's about the X.
Yes.
So why would you know it's X instead of Y?
I don't. I'm just making a choice. It could be either. We're going to find out in just a second. It doesn't matter. We can't actually, in fact, we won't be able to know that. Good question. We'll find that out in a second. All right, so let's go back to our spherical harmonic page again. I'm going to try to copy this in, and hopefully it doesn't crash. Let me save and cross my fingers. Okay, beautiful. All right, so let's go back and look at this again now that we understand, now that we've learned numbers, right? L tells me how much angular minimum the electron has, total angular minimum. And M tells me something about the direction L is pointing. All right, so again, L equals 0, the only allowed value for for M is 0, because L is 0. There's only one state with L equals 0, which we call the S state. Right, so I think more interestingly are the P's, right? That's an electron with 1 unit of angular momentum. And there are 3 M states, 1, 0, and -1, between -1 and +1. And they correspond to vectors where the angular momentum, or rather the position of the electron, is polarized along one of the 3 axes. So that's the px, the pz, and the py. And there's 3 of them, because again, M can only run between +1 and -1. And then we go to the D's, the F's, the G's, the H's, and the I's. They get consistently more complicated, right? Because we have more angular momentum. Turns out there's more nodes in the wave function. Remember, again, these are in some ways, these are waves on a spherical surface. It's the way to think about these, right? They're in some sense, they're like particle in a box waves, wave functions, which are oscillatory waves that ebb and flow and go to 0 and positive and negative, right? But these are waves that are constrained on the surface of a sphere instead. Right? Instead of in a one-dimensional box, you have waves that are constrained on the surface of a sphere. So they typically have the symmetry of a sphere. Right? And we can look at this, right? But you can, in some sense, you can embed this 2p orbital within a 1s orbital. It's like a lobe that sits inside of the sphere where the electron can exist. Right, and they get considerably more complicated as L increases, just like how as you go up in energy in a particle in a box, the wave has more and more and more periods that oscillates faster and has more nodes, more complicated structure. The exact same thing here. Like the waves on a sphere get exceedingly more and more complicated with higher and higher frequency, more and more nodes. So you get many more solutions that look much more common. Right, so these in some sense map out the possible positions of the electron in a given state of angular momentum. This is where the orbitals come from. Right, they're completely normal. It has nothing to do with electrons in general. This is just angular momentum as a whole. Anything that you spin in quantum mechanics, whether it be a molecule or an electron, around a proton, any sort of central potential, any sort of rotational problem you have wave functions that look like this. Right? A molecule that has 0 angular momentum means that the angular orientation of the molecule with respect to your laboratory axes, X, Y, Z, is totally randomized. It can be in any direction. Meanwhile, if you give it 1 unit of angular momentum, you can either find it oscillating around the x-axis, the y-axis, or the z-axis. Pointing my hand along my face. And so these are completely universal for any rotating object. They're just going to happen to be, they're just quite useful for the electron. But I myself, my PhD, my research is in rotational spectroscopy. I use microwave radiation to excite molecules using their angular momentum. I spin molecules up. Light. And the wave functions of my molecules, their angular distributions look just like this, right? They have S type, P type, D type, so on and so forth. So these are completely universal functions. these are in some sense, instead of a particle on the box, we're looking at a particle on a sphere. They have wave-like structure like the box does as well. And again, that oscillatory structure is built into the function, right? There's sines and cosines. So there's tons of oscillatory behavior inside of this. Okay. So let's go back to Monica's question, which was, why is it that I choose the Z? How do I not know it's around the X or rotating around the X or rotating around the Y? I think that's a very valid question. Why can't I just define a quantum number for rotation around the X, rotation around the Y, and rotation around the Z? Why don't I just have a bunch of boxes that measure all three? Why can't I just define everything exactly? Why do I have to choose one? And of course, that's a totally reasonable question. But unfortunately, we're limited by something that we learned at the beginning of class. This semester. So the system is chosen, right? The wave functions are chosen. Such that L squared and LZ can be measured simultaneously. Do you guys remember, did we talk maybe like a month or two ago? I don't remember. You'll have to really forgive me. Did we talk about commutators at all? Does that name term ring a bell to you guys at all? Okay, good. All right, that's fine. Good. All right, what did we learn? Let's go back to color and flavor. What I'm going to claim here is that in our the solution can be found in homework 1. If you make the following substitution. If you let LZ, this LZ box, be color, and LX or LY, you can choose either one, as being flavor, theory is almost exactly equivalent. Right? What did we learn about color and flavor? What happens when you define the color? So we have a black electron. What happens when you put a black electron into a flavor box? What comes out? You remember? Yeah, go ahead, Carol.
A white electron.
Right, a white electron. What happens when you put a black electron in? What does it come out?
Or it doesn't just flip.
Yeah, it just flips, right? So if you have a mixture, right, so you lose the information, right? So when you put a white electron in, a black one comes out. When you put a black one in, a white one comes out. And so if you have any knowledge about the color before the flavor box, you lose all of that information outside of the flavor box when it escapes. Right, so the conclusion is from quantum mechanics, it's built into the theory, explicitly defined, that only LZ, LX, or LY can be known one at a time. You know one, you don't know the other one. Right? And there's a proof that you can do. Imagine that we do 2 measurements back to back. It's a very interesting thing. So if I make a measurement, let's say for instance, I first do this, right? I first measure LZ. And then I measure LX. And then read out. All right, and then I measure LX. And then measure LZ. And then read out. And then finally what I do is I just measure LY. And then I read out. Okay, and I do this experiment in this way. All right, so what I'm going to do is I'm going to subtract the difference of the result from 1 and 2. All right, so if I take LZ, sorry, I got this the other way, sorry, LX, LZ. All right, so this is my first experiment. All right, I get some result out, and I subtract from it the result when I measure LX first. Right, and I look at the result that I get. So again, remember that we evaluate things from right to left. So here I have a wave function. I'm measuring LZ on it, get some number out, and then I measure LX on it, I get some number out. I get some result from my experiment here, and I subtract from it the result where I flip the boxes. Okay, that's all I'm doing. All right, so I'm just doing the difference between the two. The answer that you get is minus IH bar, the answer you get from Y. And this is cyclical. So if I change X and Y or Z and Y, I get the other one out. So what this is saying is that if I make a measurement along X and Z, and then I make a measurement along Z and X, and I say, hey, what's the difference between these two measurements? Well, it's different by an angular minimum vector in Y. So what's happened is imagine that my angular minimum vector is pointing in this direction initially along the y-axis, and then I measure X and Z and subtract from it X and Z, Z and X. The difference of those results is an electron that is different in this direction in Y. And it's IH bar, which means it's oscillating. All right, so what this means is that by measuring the difference between these two electrons, these two measurements is no knowledge along Y. Right, when I say, well, remember, whenever you see an I in this class, think something oscillating. All right, so when if I define something in terms of X and then measure Z or vice versa, and then subtract the opposite, I just swap the boxes, the state of the electron is different by a complex factor in the Y direction. And so what that means is that I can't know these simultaneous because I manipulate the state. Right? By taking this experiment and flipping it around, I get a result that's different. So what that means is that the electron that comes out of this measurement is different than the one that comes out of this one. All right, and the fact of the matter is that when you have this difference, it guarantees that you can't know these two things together. Right? This is guaranteed that these are not compatible. So LX, LY, and LZ are not compatible. What that means is that I can literally only know one of the three directions. I can choose one, but the moment I bring in another, I lose all information about the system. Okay, just like color and flavor. If I define the color and then I measure the flavor, I lose the color information. So that's an issue, but it's just built in, right? We saw that you can actually learn some things and do cool things with electrons with color and flavor by taking advantage of this property. It's not a limiting property. It's just saying that we have a distinct limit to what we can actually measure. And the only two things we can measure about electrons' angular minimum, or any angular minimum, is its total length, the total angular minimum, and at least one, at most, one direction. Right, let me show you what this means in terms of vectors. I think it's a little easier to see visually. Right, so imagine now, this is like the vector model. Right, imagine I have this coordinate system again. I'm just going to do it in 1 dimension or 2 dimensions. We'll just do z and x. Right, and imagine, right, so let's say, for instance, I have, let's choose a state, L equals 1 and M equals 1. Right, so if L is equal to 1, then the length of the vector is the h bar square root of 1 plus 1, which is root 2h, 2h bar. So that's the length of that's the amount of angular momentum the p electron has is root 2h bar. And if m is equal to 1, then the z component of the angular momentum is h bar. Right? So I can draw a vector that has z component h bar. Just do this just to have it nice and clean. And it has length root 2h bar. All right, so this is my angular momentum vector for this state. Right, and remember what I said is that the information along the x and the y axis is completely undetermined. So what I could actually draw, and maybe it's easier that I actually add a 3rd dimension here, just to do it, is that there are, and then there's an entire, in some sense, like cone of vectors that are perfectly legitimate. Right, I could theoretically, let me do it in a different color, right? I could also draw a vector in this direction that's perfectly allowed as well. Right, or I could draw one kind of sticking out towards the y-axis. See if I can do it. So it's got to go up to this h here. I'm just going to try to, I just need a little bit of guide here. Need a parallel line for h bar. Right, I could have one that's sticking out like this. Or I could have one sticking out towards the z-axis like this, right? There's all sorts of different choices that I can have. And in reality, the state of the electron is in a superposition of all of these states. Right? The electron can be in any state along this cone. And so this is where that uncertainty comes from, right? This is the fact, right, that we don't really understand where the electron is. We just have this delocalized ball or shell, if you will. And the electron can exist anywhere as long, right, the z component is fixed, the length is fixed, but the x and the y components are allowed to be anything they want. Right? So the electron can be in have any of these vectors. All of them are perfectly legal. Right, and so this leads to, right, so this means that in general, right, that the angular momentum in this state is polarized towards the z-axis or towards z positive. And remember, if the angular momentum vector is here, the axis of rotation, or the rotation, is perpendicular to it. So if the vector is like this, the electron in some sense is orbiting in this direction around the z-x-axis. Right, so the actual rotation of the electron is around the z-axis. Right, so when we look at the wave function for this system, when we look at psi squared for 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, we find is the 2px orbital. This is psi squared, right? This tells you where the electron is, electron probability. Right, and this is consistent with an angular minimum vector that's kind of pointing towards the z-axis. Okay, so this is consistent with an angular minimum in this direction on the z-axis. Right, because the idea is that the the x and the y components of the angular minimum vector are completely undetermined. It can be in any direction in the xy plane. But the angular minimum vector in general is pointing like, kind of like 45 or 60 degrees towards the z-axis. And that means largely that the molecule is rotating in the x plane, right, like this. If the vector is like this, then the electron is rotating in this angle. This. Right, so largely the electron is polarized around the x-axis. All right, so let's look at one more example, just to kind of drive this point home really quickly. All right, let's look at L equals 1 and M equals 0. That's something that has no z component. So I have my angular minimum vector looks something like this. It's length square root 2. This is L, right? But it could be, right, it can be in any direction in the xy plane, right? It could be pointing in this direction. It could be pointing in this direction. It could be pointing backwards. And I can just draw, a circle around these points. So the angular minimum vector can be pointing in any of these directions, right? But it's along the xy plane, right? So if the vector is pointing in this direction, the rotation is perpendicular. So the electron is oscillating around the z-axis now. This. And so the orbital that's consistent with that then, right, is a psi squared where you have probability around the z-axis, because the electron tends to be on the z-axis in this situation. We get something that looks like this instead. Right, this is the 2pz. This would be the 2px. So psi squared. Okay. So in some sense, this indeterminacy about the angular minimum of these electrons are just inbuilt into the wave functions. This lobe-like structure that the p orbitals have, and the fact that they're polarized around the three axes, is just a built-in consequence to the fact that we can't know anything about the other two directions of angular momentum. This is what leads these functions to look like this, right? They're delocalized effectively almost completely around the two axes that you're not rotating. Okay, so we don't really have to worry about the indeterminacy. It's just a fact of life. And our solutions, it's all encoded inside the solution, right? It's all encoded into the orbital structure. You just don't have any knowledge about the transverse angular minimum. And so you have delocalization, right? You have some uncertainty from the wave function in those directions. Any questions about that? Yes, ma'am.
First one.
Yeah.
Like, I don't know, I'm kind of confused, like, first how it said, like, so, like the root 2 H bar made sense, but then you said if M equals 1, then that's H bar.
Yes. Because L, let's go back to the formula again.
Oh, okay,
H bar M, so if M's one, it's just H bar.
then, like. You were saying. Could you re-explain how you did that I was pointing that way, like initially, it's like I understood video,
Oh, which one are you referring
the
to?
first one. Like when it's rotating.
How do I know it's pointing in that direction?
Yeah, like, cause well, I understand like. Well, why did you know it was like around the X, like that sort of, like rotating around the X and then.
Oh.
Those vectors around the Z.
Well, it could be also. Oh, I see what you're saying. So you're right, if I, for instance, draw. This vector in this direction, it's actually rotating around the y-axis. Right? So the only ones where it's rotating around the x-axis are the ones going in this direction. So we have to be I have to be very careful about px and py. Right? Because I've actually made a slight mistake, a subtlety. And let me explain that. All right, so let me actually make a correction here. It's not a correction, all right? It's actually just a subtlety. So let me just reiterate what Monica's noticed here. Is that I've said that if a vector is pointing in this direction, in this yellow one right here, then that means it's rotating around the x-axis like this, like I've drawn, right? But I could theoretically pick this vector, and then that would be rotating around the y-axis. Right? So there's some ambiguity there, and I haven't been exactly precise. So I think it's important that I mention this, is that there's a slight subtlety to the p orbitals. For the hydrogen atom or for any atom. And I think it's maybe worthwhile to then now let's go look at some functions really quickly. So let me pull them up. Yeah. So let's look at a few select spherical harmonics. So we'll do a little table here of L, M, in our wave function, Y, L, M. I'll try to make a plot of each one for you. So let's look at 0, 0, right? We've already seen pictures of these, right? They're the one s orbital, this is spherically symmetric. This function y 0, 0 is just a single number. 1/4 pi. Okay, so that just means that the wave function for this, the orbital wave function for the system, is just the same value at every position. Right? It's a sphere of radius 1/√4 pi. So the wave function psi squared is a sphere of radius 1/4 pi. Okay, really. So let's look at the p orbitals. So this is the s, this is p. Right, I've already plotted some of these for you last class, but let's look at them a little more carefully. 3/4 pi cosine theta. And I'll plot this for you. This is the 2pz orbital. That's cosine theta. Right, there's no phi dependence. Remember, phi is the angle that tells you about where you are in the xy plane. There's no phi dependence, so it has the same value for all phi's, meaning it's symmetric around xy. These are kind of like these symmetric lobes that have the same value at every position on the xy plane. All right, so let's look at x and y, right? So the other two functions. This is pz. I'm going to write px in quotations here, which is the 1, 1 function. We have to be very careful though, because this function, negative sign, 3/8 pi sine theta, it has e to the I phi dependence. It has a complex function. So this is a complex function. All right, what does this mean? E to the I phi that just means that, again, remember, I means, when you think e to the I, theta, think sines and cosines, a circle. Right, what this is saying is that this system is delocalized around the xy plane. Right, that's what this means. It's delocalized. Right, and it's complex. So the answer to Monica's question here is that in reality, I really don't know where it's pointing. It's completely delocalized in terms of x and y. And I don't know. It could be anywhere. All right, that doesn't really help me because then how do I call it the px orbital if it isn't really defined around the x orbital? All right, let me write the py really quickly and we'll come back to that. Why is it that I call this the px, right? Because obviously it's not localized around x at all. It's delocalized completely around phi. It can be any value of phi. So let's look at py really quickly, and then we'll come up with a solution to this problem. Problem of the p orbitals. And let me find the formula for this. Oh, yeah, correct. It's super easy. Y1 minus 1 is equal to 3 over 8 pi sine theta e to the minus I theta, e to the minus I phi. All right, so the px and the py orbitals correspond to an electron. One is an electron that is orbiting, completely delocalized and orbiting the xy plane in one direction, e to the I phi, so it has some clockwise phase to it. And then the y orbital has counterclockwise phase to it. All right, so these two x and y orbitals, they really aren't x and y orbitals in this construction. They're just waves that are moving in the xy plane, either clockwise or counterclockwise. And so they're kind of like, they're delocalized waves with positive or negative phase. Right, so that's a little complicated, right? So how the hell do I get these x and y orbitals we always talk about in chemistry? Right? If the other two m states for L equals 1 are complex, how can I have 3 real orbitals? Remember, one of the tenets, principles of quantum mechanics is that if I have two solutions to an equation, two wave functions that satisfy certain property, then the sum of those wave functions or the difference of those wave functions also satisfy it as well. Right? It's linearity. Right? If you have two solutions to the equation, the sum of the solutions is also the solution to the equation. So what I'm going to do to define the px and the py orbitals is that create combinations of these complex orbitals, make y and x. Let me show you how that works. All right, so we're going to construct 2px and 2py from the y11 and y1 minus 1 orbitals. And this is how it's constructed. The px orbital is equal to 1 over the square root of 2 times y1 minus 1 minus y11, which is equal to the square root of 3 over 4 pi sine theta cosine phi. And the py orbital, okay, good, almost done. Over the square root of 2, y1, let me get it right, minus 1 plus y11, which is, sorry, let me erase this, which is the square root of 3 over 4 pi sine theta sine phi. All right, let's plot these now. All right, by adding, the nice thing is when I add e to the I phi and e to the I minus phi, they can't, all the complex part cancels out. Right, let me show you why that is really quickly. Let's just do a quick bit of math. e to the I phi plus e to the minus I phi. Okay, how does that math work? Remember, e to the I theta is cosine theta plus I sine theta. So we have that minus cosine negative theta plus I sine negative theta. All right, so that difference is that. All right, we can now use the even and odd rules of cosine and sine. Right, cosine of negative theta is cosine of theta, it's even. And sine of negative theta is negative sine of theta. It's odd. Okay, so the way this is going to work, I can get rid of this, and this becomes a minus sign instead. And I can get rid of this. Right, and see what happens now? I get cosine plus I sine theta minus. Wait, what have I done wrong here? Hold on. Cosine theta. Oh, sorry, this should be a plus sign. I'm sorry. Plus sign, my apologies. All right. Right, so I get cosine plus cosine, and then my signs cancel out. My I sine is subtracted out by minus I sine theta because of the odd property. And so this whole thing equals 2 cosine theta. So if I divide this by 1/2, I'll lose this factor 2 and it's cosine theta. All right, so when I take a complex wave of one phase and add it to a wave going the opposite direction, I lose all the imaginary component. Okay, so that's how I can construct these real functions by using that property. All right, and so let's just really quickly kind of work our math out for these to make sure that this makes sense. So let's look at the PX. First, let's do the theta dependence, right, which is the z dependence. Sine of 0 is 0, right? So this function achieves a maximum in terms of theta at pi over 2 and pi. 0, so it's 0 along the z-axis. Right, so this function increases and decreases something like this. And it's only positive around the z-axis. And then we have sine of phi. Did I screw this up? Oh, sorry, I'm doing the first one. Cosine of phi. Cosine of phi is a maximum where phi is 0 or phi is pi. That's x equals 0 or x equals or minus x. Right, so this function lies along the x-axis. So this is our px orbital. Where we have, this is right, theta equals 0 pi, or sorry, no, that's not right. Yeah, it's max. And here phi equals 0 pi is min. Right, so this function largely lies along the x-axis. Right, meanwhile, the only difference between the y and the x is now we have a sine phi. Right, and sine phi is positive, is maximum, where theta is either pi over 2 or 3 pi over 2, which is going to be either, if phi starts from x, that's going to be either y or negative y. So the py orbital sits along the y-axis instead. So that's how we get those polarized angles, those polarized orbitals. Is that what we do is we just replace our original set of wave functions, which are the spherical harmonics, with these superpositions of these two complex waves to get a real wave instead. And these lead to polarizations along the X and the Y axis. Okay, so we get all the structure we expect to see, right? So everything that all of this indeterminacy between the different directions and things like that, all of that in terms of angular momentum is just inbuilt into the wave functions that we choose. And we don't really have to worry about it that much. We just know that the states that the electron is going to be in are going to be, in some sense, if they have angular momentum, they're polarized towards one direction. And then they have some uncertainty or some delocalization around the other two axes. Okay. What time is it? All right. So I wasn't able to get the spin yet, so we'll do spin on Tuesday, Monday. So we'll come back to spin. Spin is another type of angular momentum that the electron has that's implicit of it. Has very, very similar rules to orbital angular momentum, with just a small twist. Okay, so we'll go back to that twist on Monday. We'll look at spin. We'll be kind of comfortable. We'll be almost ready to basically dump angular momentum there. We'll start thinking about the radial problem starting Monday too. And hopefully by Wednesday, we'll have a complete picture of the hydrogen atom to start working. Have a good one, guys. Yeah, let me pause real quick. Just a
Sorry.
second. Oh, you're fine. Very excited.
Yeah, so, okay, I was